Yeah, so hi everyone. Today we got Elisa Ferreira from Max Planck Institute for Astrophysics in Garching. So Elisa got a PhD from McGill University in Montreal, I believe, and she's now a postdoc at the Max Planck Institute for Astrophysics. But soon she'll be moving back to Sao Paulo to start a permanent position there. And today she's going to talk to us about ultralight dark matter, because she recently had this review out, which you can see here, which is very nice, and is the reason why I invited her. So why don't you take it away? Cheers.
Okay, thank you very much. First of all, good afternoon. On my side, good morning. It is a pleasure to be talking to you, although really far away. So that is one of the advantages of these virtual meetings. I hope I can visit someday because I've never been to Australia, but it is very nice. Thank you for the invitation. So for those who don't know me, I'm Elisa Ferreira. I'm a postdoc fellow at the Max Planck Institute for Astrophysics. And today I'm going to talk to you about this huge topic, ultralight dark matter, which is a new and a very exciting class of dark matter models that has been re-emerging in the last few years because of the interesting phenomenological consequences. And if you want to know more about this, I wrote this review, as Siren said, which you can see is on archive already. But if you want a more recent version, you can go into the publications in my website to see a more recent version, which is the version that is going to be published in the Astronomic and Astrophysics Review. So I don't think I need to convince this audience about the about the importance and the existence of dark matter. So there's a huge amount of evidence for the existence of dark matter, spanning from all scales, from galactic scales until the very large scales. And without this evidence coming mainly from these very precise measurements of the large scales, we built the concordance model of cosmology, the lambda CDM, which is a model that parameterizes the evolution of our universe. In this model, dark matter is parameterized by the CDM, by a cold dark matter fluid. So it has this hydrodynamical description where dark matter is described by a fluid that is cold, pressureless, massive, collisionless, and it doesn't interact or interact really weakly with the rest of the baryons. And this is very successfully measured. So dark matter is very well measured in the lambda CDM, and the CDM paradigm is very successfully observationally. However, although the CDM's successes to describe dark matter, and although we know a lot about the properties of dark matter, we still don't know, yeah, my slides are slow. We still don't know what dark matter is. So although we measure dark matter very precisely, measuring the abundance of dark matter and many of these properties in a very precise way, the microphysics of dark matter is unknown. And this makes us have a huge amount of models. Here, for example, I show the masses that all these possible dark matter models span. All of those models behave as CDM on large scales, but they have very different microphysics, or they explain dark matter with very different macroscopic objects and phenomena. Like here we can see we go from primordial black holes with solar masses until ultralight dark matter with masses around 10 to the minus 22 eV, spanning 80 orders of magnitude. We are going to focus today in this ultralight, the smallest masses possible for dark matter. And also dark matter can have many properties that are not encoded in CDM, but they are also possible. So having all these possible models of dark matter that are still concordant with lambda CDM, how can we probe them? So of course we have for models that are based on particles, fundamental particles, you have direct and indirect experiments. But how can we probe them gravitationally, especially if dark matter is a different or composite object? Maybe the small scales offers us a hint on the nature of dark matter, and the small scales can give us a clue of what is this microphysics, what is this nature of dark matter. So as we can see here on the matter power spectrum of dark matter, so this is the dimensionless matter power spectrum over K. So for the small scales, which are basically much less constrained in the large scales, where we have much less observations and much more freedom yet to have different models. Different models of dark matter can give you very different predictions for the matter power spectrum. So this can tell us, this leads us to think that maybe the small scales could be a very good laboratory for us to search for the nature of dark matter. And for those properties, for those different properties that dark matter can have in those different scales. The fact that these small scales offer us hints about dark matter also can be seen from some curiosities. Some people call it challenge, some people call it curiosity, some people call it there's nothing wrong there. So it depends on who you ask. But the small scales offer some curiosities. As observations and simulations of these smaller nonlinear scales evolve, a number of challenges or a number of curiosities have emerged, challenging this coarse grain, this fluid description that we have for dark matter that is given by the CDM. This can be seen in many of the very well-known challenges like the cusp core problem, missing satellites, but also some scaling relations. So very quickly here, because I think this is all known by you all. So we have, for example, some challenges on small scales for dark matter that come from this mismatch between what is predicted by lambda CDM coming from simulations from what is observed. We have, for example, the cusp core problem, where we have an expected NFW profile gives you a cuspy core. And when you observe galaxies, you see, for example, in dwarf galaxies, in many other galaxies, here represented by the things and all things measured galaxies, you see a chord profile. So what would explain this core if dark matter given by CDM predicts a cuspy profile for the galaxy? We have also the missing satellites with this, which is this mismatch between the number of the predicted satellites that we have when we make CDM only or dark matter only simulations from what we observe. And you have the too big to fail problem, which is this mismatch between the central masses of simulated dark matter system from the observed galaxies. So if we match the abundance or the velocities of galaxies to solve the missing satellites problem, you're going to see that the simulations predict halos that are really massive and too massive to fail to produce stars and visible objects. So this is the too big to fail problem. So those problems really show us that if you have dark matter only simulations, and this can be discussed, there's a mismatch between what is predicted by the CDM and what is observed on small scales. There is another class of challenges or curiosities that are the ones that I personally enjoy the most, which are the regularity and diversity of rotation curves. So although we have a huge diversity of galaxies spanning different masses, different shapes, they are incredibly regular. And this is embodied in some scaling relations like the baryonic Tully-Fisher relation or the radio acceleration relation. And just to give an example, we have the baryonic Tully-Fisher relation, which is a relation between the baryonic mass and the circular velocity of those stars in the galaxy. And we can see that they follow here a very tight correlation. So the dispersion in some places of this plot is smaller than the uncertainty of each point, which first doesn't follow the predicted line for lambda CDM. So if it was lambda CDM, it should go with the third part of this circular velocity, but it doesn't. But what is most impressive here, it is how tight this correlation is, although this spans many different generations in mass for galaxies. And from these relations, you can have this factor that comes from observation just for fitting this curve, which is this A naught, this scale, which will be important later. So we know that dark matter should be behaving as CDM on large scales, but how do we approach these curiosities on small scales? How do we try to explain them? So I would say, maybe this is an oversimplification, but I would say there are like three different attitudes about it, which are still under debate. So the first one is that all of this can be solved by including baryons. So those simulations, when those problems emerged, they were simulations of dark matter only. So now if you include baryons, all this will go away. So you have to include feedback in those simulations. This is currently being done by many different collaborations. And the results are very promising. So apparently you can explain some of those problems, some of those small scale problems. You can reproduce baryonic Tully-Fisher, although you cannot reproduce such a tight correlation yet. So there is this discussion that different simulations parameterize those effects in a different way. So we have to wait and see if feedback alone could explain those small scale challenges. There is another very radical view, which is MOND. So MOND is a word that when everybody listens to it, everybody just, okay, shakes their head or something, but there's something really interesting about MOND. So if you don't think about the MOND theory as a theory without dark matter, a theory that is a theory of modified gravity, if you don't think like that, if you think just about the empirical force that it was coined by Milgram in, I think in the 80s, which tells us that in a system, if you are in a place where you have high velocities, it follows the Newtonian law. And if you're in a system that has small accelerations, it follows this geometrical mean between the Newtonian acceleration for baryons and that A naught, this factor that we could obtain from the scaling relations. This empirical force law, it actually describes quite well rotation curves, and it explains also explains these scaling relations. And it really presents a very curious behavior for dark matter on those small scales that it actually, it looks like that the baryons drive the dynamics on those small scales inside galaxies. Although it works really well, the way it was coined before, it was to explain this acceleration, this empirical force law, you had to impose a modified gravity theory with all dark matter, which we know it doesn't work because it doesn't fit the CMB, although there are some new models. But all I want to say that is this empirical force law is very interesting, and it would be very interesting if we could reproduce this with a dark matter component. The third attitude to solve these small scale problems, it is to modify the behavior of dark matter on small scales. So dark matter will behave like CDM on large scales, and on small scales, it will have a different behavior in a way that would suppress structure and would have a different dynamics on small scales. So although you believe or not on those small scales, I think this shows us that the small scales offer us a hint on the nature of dark matter, either if those modifications of dark matter, which will be the explanation that we're going to use to explain those small scale problems, it really offers us an opportunity to measure all those different properties of dark matter that we cannot probe with the large scale observations. So it would be very nice if we could modify dark matter in order to explain those small scale problems, or even to have a modification of dark matter that gives you predictions on small scales that could be tested with new upcoming observations. So one class of models that has the goal to do exactly what I was saying. So it behaves on large scales as CDM, and on galactic scales, on small scales, given their very, very small mass, v 10 to the minus 22 eV, this dark matter inside those galaxies is going to behave more like a wave and will exhibit a different behavior on those small scales that is going to give different predictions and different consequences, observational consequences on small scales. So the idea is that you preserve the large scale behavior as a particle that behaves as a particle, which behaves like CDM, while you have a modification of the behavior of dark matter on those small scales, giving this small mass of the dark matter particle, which means that this particle has a large de Broglie wavelength. So yeah, this is the general idea. So it behaves like CDM on large scales, like cosmological scales, but also on the outskirts of the galaxy. So if you see here, the blue represents the halo of the galaxy. We will have dark matter having this different wave-like behavior in the inner regions of the core, while it behaves mainly as CDM outside and on large scales, reproducing the observational successes of CDM. And how can we achieve this? So how can we have a dark matter that behaves differently on small scales while it behaves like particles outside this small scales inside galaxies? One way of having this is to have a very small mass for the dark matter, which could become a superfluid or a Bose-Einstein condensate on those small scales. So if I have a very small mass, this is possible that it could happen to the dark matter. So what is a Bose-Einstein condensate and what is a superfluid? So first we need to define those things so we can maybe describe those systems on these gravitational systems that we have for dark matter. So Bose-Einstein condensate and superfluid are some of the most interesting quantum mechanical phenomena on macroscopic scales. So a Bose-Einstein condensate, by definition, is when you have bosons, of course, you have to have scalar fields, and they have a high occupancy of the ground state. So if I have a gas in high temperature, where the de Broglie wavelength of each of those particles, it is much smaller than the interparticle distance. This is going to behave like a normal fluid with particles. As the temperatures become smaller and smaller, this de Broglie wavelength becomes of order of the interparticle distance until you get to a point where you get to the critical temperature of this condensate, where this de Broglie wavelength starts to superpose, and you can describe the system as a collective wave. So you can have that all the particles are now in the ground state. So you have this high occupancy. You have this macroscopic occupants of the ground state. And then you have a Bose-Einstein condensate. So the system behaves like a collective system of particles. We can see here, for example, for ideal Bose gas. So as you reach the critical temperature, the number of particles in the ground state and zero becomes larger and larger, which is equivalent of saying that the Bernoulli wavelength is of order of the interparticle distance. Another very interesting phenomenon are superfluids. They are usually associated with Bose-Einstein condensates, but not necessarily. Nowadays, we have been finding that they are not necessarily associated. But upon condensation of a system, for some systems, you can also have that the superfluid or the condensate exhibits superfluidity, which means that it's going to behave as a fluid without friction. So superfluidity is this effective dynamics that is presented upon condensation. That now the collective excitations of the Bose-Einstein condensate, they have a different dynamics now. They behave collectively, and this collective wave function has a different dynamics, which is to flow without friction. Here we can see, maybe it's not easy to see, but in this figure, in this video, you can see that when it reaches condensation, actually the water starts to go out of the cup because now you don't have friction anymore. One way of defining superfluidity was coined by Landau, which describes that a superfluid can happen if you have the existence of condensate. So superfluidity happens upon condensation. And if you have a system that has a critical velocity, and only for systems that are have subsonic velocities, so velocities that are smaller than the critical velocity. So if in this way, you can describe your system of two fluids. So you have the normal fluid, which is the fluid that is not condensed, and the fluid that is the superfluid. So at T equals 0, everything is a superfluid, but if you have a different temperature, you have a combination of Hello? Hello, can you hear me?
I can hear you. You dropped out for a few minutes
yeah,
though.
Oh, really?
Yeah, you dropped out for maybe like 20 seconds or something.
I apologize for that. Do you know where I stopped?
Elisa, it's very good, but maybe you can try to mute the video. So you're cutting out sometimes the voice, so it will be better. If hopefully, thanks.
So if I take my video off, you mean?
Yeah.
Okay, just a second. I'm not finding the. Okay, I apologize for that. So can you see my presentation again?
No. You need to share that again.
So let me share again then. Yeah, I'm using my cable connection, so I thought it would be okay. Can you see the presentation now?
Yeah, it's all good.
Yeah.
Yeah. So did you hear about the superfluid?
Yeah, that's where we got up to, I think.
Okay, good. So as we define BEC and superfluid, now we need to know how to describe those systems. So the description of a superfluid and a condensate is that if I have a pure BEC, this is described by a non-interacting many-body system of bosons. So if I have a Bose gas, like a bunch of bosons not interacting, this if you decrease the temperature, this will give you a BEC. If those are interacting, those bosons are interacting, this will give you a superfluid. You have a condensation, you form the BEC, and this BEC has the property of being a superfluid. The dynamics of this system can be described like this many-body Hamiltonian of any interacting or non-interacting bosons. This is a very complicated system to be solved, even for very simple potentials, because you have multiple fields, and this is a nonlinear system. So most of the times we use the mean field approximation, which can be used if you have a large number of bosons, and if they're dilute, which means if the interactions between them are not strong. And in this mean field approximation, you basically, instead of describing each of those as different waves, different many-body system, you're going to describe as one body system, which has a macroscopic wave function, which is given by this part, which is the expectation value of the quantum wave function. And I'm going to call this like a classical field or a classical wave function, and small perturbations on top of it. If I use this mean field approximation, I can describe then my superfluid and my BEC by the Gross-Pitaevsky equation, which is this nonlinear Schrödinger equation. Nonlinear because we have this vector, and here I put in a trapping potential, but you can have a trapping potential or not. And this describes the evolution of this condensate in the mean field approximation. You can also think about condensation as a phase transition. So you can think that when I was in high temperature, my bosons are in all the possible states, energy states that we have. And as the temperature goes down, all these bosons are going to go to the ground state. So you can see this as a phase transition. And and it's very useful for phase transitions to use field theory description to describe a phase transition. So we can describe then this many boson system as a weakly interacting Bose system that has particle conserving number that had a spontaneous breaking of a U1 symmetry. Which is the symmetry U1 as the symmetry of the many-body Hamiltonian. So we can describe then a condensate or a superfluid. So it is a superfluid when we have interactions, when these terms are present, and it is only a Bose-Einstein condensate if I don't have these terms and I have only this part. So this system of a scalar field with a U1 global symmetry can describe a condensate where this ground state breaks spontaneously breaks this U1 symmetry. And in this breaking regime, where we have this, this mass here, which is a combination of the mass and the interaction, when it's bigger than the mass, you have Bose-Einstein condensate. And when it's smaller, you have the symmetry restoring phase. So that is how we can describe the condensate. So the condensate is going to be the ground state that spontaneously break this symmetry. And it is, because of the symmetry, is a complex scalar field that has this phase and also this phase, and this amplitude. Because the current is constant, you're going to have that This phase is given by mu T, where mu is the chemical potential. You can have excitations on top of this condensate here, as we can see, and those collective excitations are given by the massive quasiparticles, which are the excitations of the amplitude, and also the massless goldstones, which are the excitations of the phase that are created by this spontaneous symmetry breaking. So at low energies, we can integrate out these massive excitations. They are not important. And the system can be described only by the excitations of the phase, which are the phonons of our system, are known as phonons. And they behave like a wave. They propagate as a wave when you have condensation. And they can mediate long-range forces. So by having this Lagrangian with this spontaneous symmetry breaking, you can, if you take the non-relativistic limit of this system, you can reproduce again the Gross-Pitevsky equation, the same one that we obtained by the quantum mechanical Hamiltonian. And we can also rewrite the system in a fluid description using the Madelung transformations, where I say that the phase is going to be a velocity, and then the field can be described by this density rho. And then I can describe my system, this Gross-Pitevsky equation, as a system of equations that has a continuity equation and an Euler-like equation, where we have a pressure here coming from the interaction term. So depending which interaction you have here, you have a pressure term that it could be attractive or repulsive. And there is a different term that doesn't appear in fluid equations, which is the quantum pressure term. This is not actually a pressure, but this term is historically coined. And this is going to give the different behavior of the system. So the different behavior of the system, this term is very important for it, because this term is always going to be counterbalancing, for example, gravity, as we have in the dark matter. So I described the most simple system for you, this most simple condensate, which is as weakly interacting superfluid. But I can have more complicated superfluid systems. For example, I can have something called unitary Fermi gas, which is a system that has an equation of state that goes like this. And those systems, or even systems that are not not weakly interacting, they cannot be described by this microscopic description that I presented in this Lagrangian. So you have an effective field theory for the superfluids, effective way of describing this, which at low energies is a theory for this phonon. And this phonon exhibits shift symmetry that is inherited from the U1 symmetry of the complex scalar field. And this tells us that I can write then my Lagrangian for the superfluid as a P of X Lagrangian, since I have shift symmetry. And this X I can write in first approximation in low energies as the first derivative only of the field. And since I want Galilean invariances, I'm in a non-relativistic system, I can also have the gravitational potential or end potential here. So this description gives us the description for BC, the normal BC that we had before. If I have n equals 2, for example, if I have a power law for my P of X, but it could also give you different systems, like we're going to see later, that if I choose n equals to 3/2, I can reproduce the Mond behavior by having a superfluid. So after this long introduction on superfluidity and Bose-Einstein condensate, we can go for our ultra-light dark matter models. So again, the idea that we have is that we want to reproduce CDM on large scales, maintaining the observational successes that CDM has, while on small scales, I want this non-CDM behavior. So here we have two things happening. So first, we're going to have a suppression of the power spectrum or of growth given by these different initial conditions that we have from this system that produces a core on galaxies. And also inside this core, we're going to have a non-CDM behavior. So inside those cores of galaxies, we're going to have the dark matter is going to behave more like a wave than behaving like a particle outside the cores of those galaxies. So like I said, these models have been receiving a lot of attention in the past few years. They are not new, but there is they have regrown in the last few years, and they received many, many different names. And you can see all these names in the literature, and they can be confusing. But they actually can be divided into 3 categories, and this is what I show in the review, and I'm going to show you now. So these 3 categories can be divided, can describe the different behavior that these models have on small scales. So here I'm not dividing into categories of fundamental particles, if it's an axion or axion-like particle. This is not the type of categorization I'm doing. What I'm describing is like how those different systems are going to describe different behaviors for dark matter on small scales, and they're going to also have different observational consequences. So the first class is what I will call fuzzy dark matter, but it can also call wave dark matter, psi dark matter. But I chose to call this fuzzy dark matter because fuzzy dark matter is already a very well-known and used name for this model. And this describes this ultralight dark matter that is only under the influence of the gravitational potential. So I have no self-interactions, which is equivalent to the BEC system I showed before. I also have the self-interacting FDN, which is exactly the same system, but with a weakly self-interaction, that it could be a two-body self-interaction or a higher order interaction. And this is equivalent to the weakly coupled BC I showed before, which is the simplest model of superfluidity that it can have. And the third class of models are models that I'm going to call superfluid dark matter, although this is also superfluid. This is a more general superfluid model. And this model not only has a different behavior on small scales, but also this reproduces MOND on small scales. So not only you're going to have a suppression of the power spectrum from these models, but also inside the cores of those galaxies, you're going to have the dark matter behaves in a different way. It behaves like MOND, which is what is necessary to explain, for example, the scaling relations that we have. So how light is ultralight? And why do we have to have dark matter in this range that I showed before? So we want dark matter to behave as a wave on galactic scales. So what would that mean? This could mean 2 things. This could mean first, that I want, if this is the halo of my galaxy, I can say that I want that the behavior of dark matter as a wave, it's only inside the halo of the galaxy. So I don't want clusters to be behaving like dark matter. I want only galaxies to like waves, sorry. I want galaxies only. So if I do this, if I have this requirement, I can either have that the de Broglie wavelength of my dark matter is of the order of the radius of the halo. And this gives you the lower bound of 10 to the minus 22 EV. Or I can say that I have the superposition of the de Broglie wavelength of each particle. And this superposition needs to be of order of the halo size. So to have particles that superpose and form a collective wave that is of the size of a galaxy, we need to have the dark matter has to have a higher bound here of EV. So when I'm in ultralight, it could be anywhere between this EV and 10 to the minus 25 EV range. So first I'm going to describe the first two models. So the self-interacting fuzzy dark matter and the fuzzy dark matter, which are the models that have this microphysical description given by this action, the weakly self-interacting action in the case of the self-interacting dark matter. And in the case that I don't have this interacting term, the fuzzy dark matter model. So this class of model is a class of model that is described by this action. It is a very generic, I'm not saying that it's associated with any microphysics, but if I have an axion or an axion-like particle, those are going to be inside this category of ultralight dark matter because they have exactly this microscopic description. So fuzzy dark matter and self-interacting dark matter are a huge class of models that could be phenomenological models, but they also include axion-like particles, for example. The evolution of this model is the following, is given by this equation of motion, which basically tells us that the asymptotic behavior on early times, where this term is important, when the mass is smaller than Hubble, it behaves as a constant, so has an equation of state as dark energy. And at late times, where the mass term dominates, it oscillates. So it has an average equation of state as matter. So we can see here that, for example, in the evolution of the field, at early times, it's a constant and then oscillates, and it behaves as dark energy at early times and has an average equation of state as dark matter. So if you want dark matter if you want this ultralight field to behave like dark matter, we need that those oscillations start before matter and radiation equality. So for that to happen, I need to have a mass which is bigger than 10 to the minus 28 eV. So if I have a smaller mass than 10 to the minus 28 eV, it's going to behave as dark energy already at the CMB, already even before the CMB at equality, and this will change the behavior, this will change the evolution of the universe. And this component will not behave as dark matter, or you're going to have a very different model. So we need to have the mass within this range. So it needs to be bigger than 10 to the minus 28. So this is the action that describes this class of models. We're interested in the behavior on small scales, so we're interested in the non-relativistic regime. And if I go to the non-relativistic regime, I recover again my Gross-Pitayevsky equation, but now the Gross-Pitayevsky equation in an expanding universe. And this is the Schrödinger equation, the nonlinear Schrödinger equation that describes the evolution of the fuzzy dark matter and the self-interacting dark matter. I can, but this equation in the case of the systems that are under the influence of gravity is coupled to the Poisson equation. So this is the system of equations that describe the self-interacting dark matter and the fuzzy dark matter. So just to recall, if I have no interaction, this is the fuzzy dark matter, and if I have an interaction, either attractive or repulsive, I have this self-interacting dark matter model. And those models are going to have a very different phenomenology. So as we can see, for example, now, so if I want to study what is the core, what is the profile that I'm going to have for this system on small scales, I can, for example, study the stability of this equation. So by studying the stability, so by finding where those modes are stable or unstable, which means where I have solutions that grow exponentially and where I have solutions that are oscillating, I can find this by knowing where the dispersion relation is equal to 0, and I find this wave number, which is exactly like we do for genes analysis. And we can see here that I apologize, here there's a mistake. This should be bigger than 0, and this is smaller than 0. I apologize for that. So for G bigger than 0, which means repulsive interaction, the solution of this equation oscillates for all Ks and is stable. So I can have a stable core inside my galaxy of any size. So if I have G is smaller than 0 or an attractive solution, I'm going to have that for, I can only have a stable solution inside a region inside my halo of a galaxy. So I cannot have that my entire galaxy, for example, it is forming a condensate, or it is this core dark matter is described by this condensate. So for attractive interaction, it can only form very localized clumps. So you can never have really attractive self-interacting dark matter really describing a dark matter that behaves different in galactic scales. Here we can see, for example, for the QCD which has 10 to the minus 5 mass, the size of this soliton would be 10 to the minus 5 kiloparsec. So this would be very small, compact, localized clumps, and they cannot be the cores of the dark matter. So the negative interaction, so the attractive interaction doesn't work to describe dark matter. So if you have fuzzy dark matter, so you don't have interaction, you have just a system under gravity. You can calculate the Jeans length of this system. And you have that gravity dominates, and this is unstable for scales bigger than the Jeans length. So outside the Jeans length, this is going to suffer gravitational collapse and behave like normal CDM, while inside the Jeans length, quantum pressure dominates. So the solution is stable and you don't have structure formation. So this means that you're going to form a core inside the galaxies where you don't have gravitational collapse. So this is summarizing the different behaviors, so the different phenomenology of those models. So for the self-interacting FDM, you can only form localized clumps for attractive interaction, and for the fuzzy dark matter, you can form cores of the size of the Jeans length. So that is the picture that we have then for fuzzy dark matter, for example. I'm going to discuss fuzzy dark matter because this is the most famous model that we have. So the idea is that this is the core of your galaxy. So this is, this is going to behave like CDM outside this core, and also in the outskirts of this core for any scales that are bigger than the Jeans length. And you're going to form a core here where you have no structure formation that you can have inside the Jeans length, which we call usually Bose star. And sometimes people call it that you can form a soliton inside. There is a huge debate if there is actually condensation happen here. So until now, we only showed that I'm going to form a stable region inside the inner regions of my galaxy. So does this mean that I reach condensation in this point? Or does this mean that I only have a region where I have a different gravitational collapse than the rest of the halo of the galaxy? And this was shown in a work by Levkov in 2018, and a work from this year, where they did simulations, and they showed that without any seed, you can actually have the formation of Bose-Einstein condensate cores only under the influence of gravity. So we can show that actually we can have inside those regions of those galaxies the formation, the formation of a core, and this core can have a condensate, can be in a condensate, could form a condensate, a Bose-Einstein condensate. And then this can have a lot of consequences, observational consequences from how dark matter behaves. So those cores can be seen in simulations. For example, we have many groups doing those simulations. And with those simulations, we can find the profile that you have for those cores formed in the inner regions of galaxies and the radius that is expected for those cores. This is a simulation by Skivi for a 10 to the minus 22 mass. And for a galaxy, a Milky Way-like galaxy. And they find in the simulation that you can form these cores that have this profile and this radius. So the idea of this model is really that in the outskirts of the galaxy, it's going to be described by NFW profile. So it's going to be described as a CDM halo. But in the inner part of the core, you're going to, of the galaxy, of the halo of the galaxy, you're going to form a core. And this core is going to have a density like this, that is very different from the NFW. And this can be seen here in this plot. And for example, if I have a Milky Way-like halo that has 100 kiloparsec of size, the halo, we can see that the size of this core is approximate 0.16 kiloparsec. So it's really in the inner regions of the galaxies for the fuzzy dark matter model. So this is the fuzzy dark matter model, the idea of the model. So if you really want to have sizes of this core that are interesting, that give you an interested size core here, I have to have that the mass of this dark matter is between 10 to the minus 22 and 10 to the minus 20. Even 10 to the minus 20 gives you a too small core to have an interesting consequence. But within this range, you have a big enough core in the center of the galaxy that can give you observational consequences. And this is what we discuss now. So the first consequences that we have for having this core, for having this dark matter with such a small mass, is that you have a suppression in the power spectrum, since you have this, now you have this Jeans length. So we can see here, for example, for the matter power spectrum, you can have a suppression on small scales depending on the mass. And this also can be seen in the halo mass function, which are also going to suppress the formation of halos of smaller mass. So in the FDM model and in all these ultralight dark matter models, I'm going to suppress the formation of small halos or small subhalos. And this could be, for example, something that solves the missing satellite problem. So the presence of this core also can have consequences because you have a different profile for dark matter in the inner region of the galaxy. And also the fact that you have a Bose-Einstein condensate, or that you have this wave now describing, can have different dynamical effects. We can use these observational consequences to put bounds on the mass of the particle. So for example, here using the large scale structure, more or less, we can see that if I use CMP, I can only put a bound in the mass, that the mass needs to be bigger than 10 to the minus 24 eV. This is if I want 100% of the dark matter to be fuzzy dark matter. So if I'm in this region, for example, I can still have dark matter even with 10 to the minus 28 eV, but the fraction given by here in the y axis, it must be much smaller. So I can only have 100% of dark matter if I have masses that are bigger than 10 to the minus 24. However, lately, we had some analysis using Lyman alpha forest that shows us that the mass of the dark matter needs actually to be bigger than 10 to the minus 21. And there's even a new analysis that tells us that it needs to be bigger than 10 to the minus 20 EV. We can also use the fact that there is a core in the center of the galaxy to constrain the mass. So for example, we can use dwarf galaxies. We can measure the density of those dwarf galaxies and compare with what is predicted by FDM. And we can put a bound in the mass of FDM in order to have a core. I'm going to skip some of the, and this would solve the core problem. Also, as I said before, since you have less small halos, so if I have a 10 to the minus 22 EV mass, I'm not going to form small halos. So this can maybe solve the missing satellite problem and the too big to fail. There's also interesting dynamical effects. So now, since my FDM is not described by particle anymore, but by this macroscopic wave function, there's a relaxation between this macroscopic wave function and macroscopic objects, for example. I can think, for example, that now I have this effective mass for my fuzzy dark matter, which is, but actually you have this, actually what you have is that FDM is given now by this wave function. And what this could cause is either cooling or dynamical friction. So I can think that now my FDM has this, could be thought as this quasi-particle with a bigger mass than the mass of the particle. So I can effectively think as a collision between those macroscopic objects like stars or star clusters with this FDM fluid. And this, depending on the mass, this can either cause cooling or heating. And this can give very interesting phenomenological consequences, like the dynamical friction is very different and can explain, for example, the survival of fornax and other effects that I don't have time to talk now, but I'm happy to talk later. And I can compile, for example, all these different consequences for fuzzy dark matter and the constraints that this gives by different measurements. So here we have, for example, CMB that we talked about, Lyman alpha. We also have Eridanus 2, which is a star cluster, which can be constrained by these dynamical effects. We have dwarf spheroidals, dynamical friction, heating, and all of those, these regions are the excluded regions for the mass. This is black hole superradiance. So this has nothing to do with all that I talked about now, the dark matter forming cores or anything. This is only the creation of these ultralight particles by rotating black holes. This also puts bounds on the mass. So these regions are not allowed by stellar mass black holes and by supermassive black holes. So we can see from this plot that I said that the interesting range for masses is 10 to the minus 22 to 10 to the minus 20. We can see that this range of mass is pretty much constrained by now. Of course, all of these measures depend on a lot of astrophysics, and they might not hold. But we can see that many different measurements that come from many different effects, some are from Jeans length analysis, some are from dynamical effects. They are all pointing out to that this fuzzy dark matter, so the simple model without interaction, probably cannot have this smaller mass. And if you go to higher masses, then you lose all this interesting phenomenology because the core is going to be too small to have any interesting effect. It still has some interesting effects, but not as interesting as before. But again, I should stress that this bound might not hold, but this is an interesting result. So do I have 5 minutes, or should I skip this?
Yeah, you can go 5 minutes. I mean, people.
Okay, I promised just 5 minutes. We can now talk about the last model, which is the superfluid dark matter, which was developed by Garching and Justin Curry. And the difference from the previous model is still have a core in the inner regions of the galaxy, but this core now is described by a different superfluid, which is given by this effective field theory of superfluidity. That gives you a Mond dynamics on galactic scales. So I call this Mond for phonons, but it's like Mond for dark matter. So it's dark matter behaving as Mond. So in this approach, I can use effective field theory of superfluids to describe my superfluid, my dark matter, by a P of X action. If I want this to give me Mond, then this P of X needs to be given by this X to the 3/2 term, which leads to an equation of state like this, which is exactly what you need for Mond. So this is phenomenological. So we say that given that we have the freedom in the effective field theory of superfluids to give my action, I'm going to choose this because I know this reproduces Mond. Unfortunately, this is not enough, and you have to add a phenomenological coupling between the phonons and the baryons, which is given by this term. So by having this Lagrangian, so that is this P of X plus this interacting, you can have that this theory is described at large accelerations or at large potentials here, gradients, by a Newtonian dynamics, and in low gradients regions, like inside the galaxies, the cores of galaxies, it is described by this modified relation, which is exactly Mond, exactly reproduces Mond. So just so we understand the scales a little bit better, so in this model, inside galaxies, so inside the inner regions of galaxies, I'm going to be in this limit. So it's going to be described by Mond. In the outskirts of galaxy, I'm already in a region where it is described by Newtonian limit. Outside galaxies in clusters, for example, the gradients are too large. So I'm going to have mostly particle dark matter in the Newtonian limit. In the large scale structure, I have that it is actually condensed, so actually a superfluid, but it is still going to be in the Newtonian limit. And on solar system scales, it's not going to be given by Mond, because in solar system scales, you're violating the Landau criterion, and you have supersonic speeds around stars. So you're going to be in the Newtonian limit, not violating any of the measurements that we have on solar system scales. So this is the idea. In the center, I have a superfluid core, and outside the skirts of, you have an CDM-like behavior. And this explains quite well rotation curves. I cannot go through in details here, but we can see that for different types of galaxies, this model reproduces the rotation curves quite well by having a superfluid core, which is smaller than the halo of the galaxy. Here we can see for low surface brightness galaxy, and here for a high surface brightness galaxy. There's many different interesting consequences of this model, and I invite you all to take a look at the review or the articles by Justin and Lasha. This model really gives interesting phenomenology, phenomena in galaxies, especially dynamical friction. This is very interesting because a superfluid, it is a fluid that flows without friction. So how does a galaxy that has in the inner cores behaving without friction works? So this is very interesting. Sorry, I'm skipping some of the things here. So if I have a superfluid, I can have vortices, which means that, like I said, a superfluid is something that flows without friction. So if I rotate a superfluid, how am I going to have this rotation, since the superfluid is an irrotational fluid? So the way a superfluid rotates actually is by forming vortices. So these vortices are quantized, as you can see here, in a measurement done in a condensed matter system. And those vortices, they carry all the angular momentum of the system. So if I have the dark matter is described by a superfluid, I should have the formation of vortices in galaxies. And it would be very interesting to see how many vortices that you would form and how big are they. We have a very simple estimate here that if I have a halo that is 100 kiloparsec, more or less like the Milky Way, I would have 10 to the 23 vortices that are of order of millimeter. So this would be very hard to be measured, but this is very rough estimate. I have been working with this amazing PhD student, Garching, by doing simulations of the formation of those vortices for different interactions and different densities in the halos of galaxies. So I think I'm going to stop here, and I hope I have convinced you that this class of models has a very interesting phenomenology in galaxies. There are many different descriptions of those models coming from this well-known condensed matter systems. There is a big effort in constraining these models, which already shows here for the FDM, which really challenges the masses that are the interesting masses for these models. But there's a lot of work still to be done for the dark matter superfluid and for the self-interacting model, and even to verify the fuzzy dark matter constraints. So sorry, I went a little bit over time, and thank you very much.
Thank you, Lisa. That was great. I'm conscious a little bit of the time, but I think we should take some questions. If anyone has a really burning question, please just jump in and ask it. Yeah.
Can I ask one question?
Yeah, please.
So thanks for a very nice talk, first of all. Can you comment a little bit on the reliability of those limits on fuzzy dark matter?
Oh, yeah, that's a very interesting thing. So, yeah, so for example, let's get the Lyman alpha, which is one of the most important constraints that we have now. So the Lyman alpha really depends a lot on the intergalactic medium, how you really are going to model this. And this is depending on the simulations and all the hypotheses that you make in the simulations. So really good groups have been putting bounds on this, but I think they leave it really clear that it really depends on how you model this intergalactic medium, this IGM. Yeah, so I think we have to wait for more simulations, and maybe, I don't know, they all use the same data, but I think it depends now on how the simulations. Mm-hmm. So for the dwarfs, I think this is really interesting, and we have this new result that we're going to publish probably next month from ultra faint dwarfs. Again, it depends on how you model them. It depends on how you describe the core. For example, we use the core profile that is obtained from simulations. And we know that those simulations are not cosmological simulations. Those are simulations of like 2 or 3 halos. So they might be wrong. So it might be that we're using a profile to obtain a mass that it is not good. Yeah, this is are some. I really like the dynamical friction and heating. this this heating one depends on the, this is for the Milky Way. So you see, if you have this heating, if you have, for example, stars interacting with FDM, this heating can make that the bar of the Milky Way becomes thicker.
Okay, because you just put energy in and then it's...
Exactly, you inject energy and then it becomes thicker. So it gives you an interesting, it's not competitive with the others, but it's an interesting constraint as well.
So how much can those bounds vary? What do you think? So is it more like
yeah, so,
order of magnitude, or is it, could they go away completely, or some of them?
So for the Lyman alpha, I've never done this analysis myself, but I heard that you can really change one order of magnitude by changing some parameters of your simulation of the IGM. What we have been doing for the dwarfs, we can really see that if you change the profile a little bit, your constraint, the error bars become really huge. So I'd say, for example, here for my ultra faint dwarf, that's what I understand because we did this. If I don't use this profile, or if I use a different profile, this could really become an error bar that is like 1 or 2 orders of magnitude bigger, allowing again the mass range, interesting mass range. So I think we should take this with a grain of salt. It can really change by order of magnitude. But at the same time, we have from very different measurements, they are indicating that not the entire mass range, but at least 10 to the minus 22 for me, it seems to be very challenging. Because it's really, I don't know, I don't see Lyman alpha really like 2 orders of magnitude change. And also you have Eridanos, you have dwarfs, you have 21 centimeters. So all of them are really challenging the 10 to the minus 22. It would be very interesting if someone comes up with a method that doesn't depend on astrophysics that much. So I would say that the 10 to the, in my opinion, my personal opinion, the 10 to the minus 22, it's a bit challenging.
Yeah, thanks a lot.
Thank you.
May I ask just very quick question? Heating, what heats what? Is dark matter heated or star motion is heated?
Yeah, so maybe I have a slide here. Sorry, I don't have more on that. I was very fast. So, so when the stars interact with these fluctuations of the FDM field, if the masses of the star are smaller than this effective mass of the superfluid is going to inject energy in those stars. So the stars are going to heat. So they're going to have bigger velocities. And then this can, for example, heat or make the Milky Way disk thicker. So this is the heating. But if I say that my macroscopic object has the mass that is bigger than the FDM fluctuation, then actually the macroscopic object loses energy to my FDM field, and then I have dynamical friction or cooling.
Thank you.
So these two effects can give you a bound on the mass. And it depends also on the macroscopic object. So here for heating, this is the heating of the Milky Way disk. It's actually really stars. So you get one, the macroscopic object is a star. You can also use, for example, a cluster of stars or even black holes. And then you see if they are cooled or heated.
We had a question in the chat, which I'll read out for the purposes of the recording. Can you talk about what happens if you have ultralight dark matter coupling to the standard model in some way, e.g. through photons?
Yeah, so thank you for asking this. So in my review and also in this presentation, I was very agnostic about what this is. So I'm not saying it's an axion or an ALP. Of course, an axion and ALP are going to be inside this fuzzy dark matter model. But indeed, depending on the microscopic model that you have, depending on what you think this dark matter is, you could have couplings with the standard models, and there are many searches for this coupling with photons, for example. And these searches, they probe very different masses for this axion or this axion-like particle, also depending on the type of coupling. So yeah, this is a huge field that I didn't talk about. This is another way of maybe probing this small mass axions, this small mass axion-like particles. I focused on the gravitational parts, but yeah, you can also have those interaction with the standard model, and especially the interaction with photons. It is something that it is the target of many, many different experiments. I have many references about that in my review, although I don't talk about that in details.
Yeah, great. Maybe I'll just ask one last question. So, I was quite taken aback by the fact that there are so many constraints, looking like they're ruling out the interesting mass window. But as well as this astrophysical uncertainty business, there is also the possibility. I don't know if this question has a very good answer to it, but one of the models, one of the places where we could think about getting like particles of this mass would be from the axiverse, from string theory, where you would have the whole spectrum of loads of axion-like particles with very, very low masses, in which case plotting a single axis like this is less trivial. Like you might have a spectrum of different masses, so what exactly is the mass that you're constraining? I don't know if anyone has looked into this, and if there is any like qualitative differences in the types of structures that you end up with, or if it's just a complete mess and you're not able to really say anything. But have you heard of anything like that?
Yeah, that's a very good point. So, so two things. First, you're completely right. In this plot, for example, I'm assuming many things. I'm assuming that I want 100% of the dark matter to be whatever this ultralight thing is. So, for example, you could have a y-axis here that is the fraction, right, of the dark matter, and then it would be a very different thing. There is an interesting review that has this plot. So it is fraction over mass, and then it has some constraints there. And like you said, it's more complicated. So for example, if I have axions, this mass and this coupling, they are, you'll know the relation between them. But if I have Alps, for example, you could have different couplings for different masses. And this could be written as this, for example, this fraction of dark matter. So I think this plot is really interesting. I can send you, or I can put in the links, the review that has this, this plot, which is just, yeah, like you said, it's fraction over mass, which maybe you could rewrite for an Alp, for example, if you want to specify what is the microphysics of this particle, right? You could maybe have a plot for the interaction over mass. Yeah, I've only seen I never seen like a complete one. Like this, like really the latest observation for mass and coupling. I only seen mass and fraction.
Yeah, and I guess
so pretty interesting.
Those constraints assume that at every point on that plot, you're just assuming that the dark matter is just all in that fraction at that single mass. Whereas I guess
exactly.
You, in the same way that you do with like people like recast the primordial black hole constraints in the context of like extended mass functions, you might be able to do a similar thing in this context where you recast like ultralight axion constraints in terms of like a, so to say, you know, from string theory, you had some spectrum of axion masses. I guess the interesting question would be is if there is a spectrum of masses which would end up relaxing these constraints into the point where you have an effective mass which is around, which is in the interesting window and also circumvents the constraint somehow.
That would be very interesting. Yeah, I think this is so new. Like this plot, this type of plot that I'm showing here with all these constraints is so new, and I think just now we're getting to the point that we are okay. 100% for 10 to the minus 22 doesn't work. So maybe we should think about something like you're thinking. How can we relax this? I think that's the new game actually in this type of models. So it would be very interesting to have something like that.
Okay, so I think that's probably a good time to start recording.